Changes in gravitational potential energy. Close to the Earth's surface, the gravitational field is almost uniform, and so the change in gravitational potential energy in moving through a height delta h is simply given by mass times gravitational field strength g times delta h. If we plot a graph of weight, or mass times gravitational field strength, against the distance from the Earth h, we would get something like this. Weight doesn't change with small increases in height above the Earth's surface. This would apply as long as the height is very small compared to the radius of the Earth. We're already 6,400 kilometers from the centre of mass of the Earth, and so going to the top of a tall building, or even to the top of a mountain, has negligible effect on the gravitational field strength. If a body is raised from this height to this height, a distance delta h, then the change in gravitational potential energy is equal to the area under the graph of mg against h, as the area of this is going to be mg times delta h, which, as we said here, is the change in gravitational potential energy. At bigger distances, the reduction in field strength must be taken into account. It obeys an inverse square law, meaning if we double the separation, we reduce the field by a factor of 4. If we plot a graph now of weight against distance from the Earth, which this time I'll call r rather than height h, we would get something like this. If we again raise a body from this separation to this separation, a distance delta r, the change in gravitational potential energy is again the area under the graph of mg against r. The change in gravitational potential energy can be calculated using this equation. You're not expected to be able to derive this equation at A level, but you are expected to be able to use it. It will be given on your data sheet. It tells us the change in gravitational potential energy is equal to the gravitational constant multiplied by the mass of the stationary body multiplied by the mass of the moving body, and this would be the separation at the start and the separation at the end. Let's look at a very simple case of two separations of 2 units and 4 units. Well, in moving out from 2 units of separation to 4 units of separation, this part of the equation becomes 1 over 2 minus 1 over 4, giving an answer of plus a quarter. This is a positive number, showing a gain in potential energy, as you'd expect as we move the bodies apart. Moving in from 4 units to 2 units, we get this becoming a quarter minus a half, which is equal to minus a quarter. This is a negative number, showing a loss of potential energy as the bodies move together. Let's look at a more complicated example. Find the change in gravitational potential energy for a 500 kilogram satellite when it is raised from the surface of the Earth to a height of 4,000 kilometers. We're told to take the mass of the Earth as 6 times 10 to the 24 kilograms, the radius of the Earth as 6,400 kilometers, and the gravitational constant as 6.67 times 10 to the minus 11 Newton meters squared kilogram to the minus 2. First writing out the equation, then we can add the numbers for the gravitational constant, the mass of the Earth, the mass of the satellite, the initial separation being the radius of the Earth, and the final separation being the radius of the Earth plus the height of the satellite above the Earth's surface. We can do this part of the calculation first, which comes out at 6.0 times 10 to the minus 8, and that will be meters to the minus 1, and this gives a final answer of 1.2 times 10 to the 10 joules. This is a positive answer, as the satellite will have gained gravitational potential energy.